Hi everyone, in this video I want to talk about intervals of convergence. So we want to find the intervals of convergence for f of x and the integral of f of x, where f of x is given as the series. It's the sum as n goes from 1 to infinity of -1 to the n plus 1 power times x minus 4 to the nth power all over n. So to attack this problem, I just want to remind you here of the ratio test because that's the test I'm going to use. So I'm going to use this ratio test for series, and I'm going to look at the ratio of my terms. And if the limit of the ratio of the terms is less than 1, I've got absolute convergence. So I'm really hunting for what values are going to make this series converge. Because it's going to converge some places, but probably not everywhere. You might get lucky, it might converge everywhere, but usually that's not the case. All right, so let's take a look here. I'm going to do my limit as n goes to infinity of a sub n plus 1. So I need everybody in here, and I'm doing absolute value, so I don't even care about -1. I'm going to do x minus 4 to the n plus 1 power over n plus 1 all over x minus 4 to the nth power over n. So I've got a fraction of fractions here. All right, so let's tidy this up a bit. I've got the limit as n goes to infinity of, if we simplify the x minus 4 powers, I have only an x minus 4 to the first power. And you might ask yourself, why is that the case? Because I've got essentially x minus 4 to the n plus 1 over x minus 4 to the n. And if I subtract those exponents, I'm just left with 1. I got one of them. Okay, now in the denominator here, what's going on with the n plus 1 and the n? If I multiply top and bottom by n, these puppies cancel, and so I've got n over n plus 1. Okay, and now we're going to do the limit. So x minus 4 has absolutely nothing to do with the limit as n goes to infinity. So I can pull that out in front. I've got the absolute value of x minus 4 out in front. And now the limit as n goes to infinity of n over n plus 1. That's just going to be 1. So I've got x minus 4. So what's going on here? I wanted, in my heart's desire, I wanted this limit to be less than 1. I wanted this limit to be less than 1. In other words, I worked it out so that my condition for convergence is that I want absolute value of x minus 4 to be less than 1. And if I can guarantee that, I've got absolute convergence by the ratio test. Right? So I'm cooking up a problem. I really want convergence. I mean, that's really what I'm hunting for. So let's just make a little bit of space here. I'm going to keep working. So let's come on over here. Oops, that is not what I wanted. Let's come on over here. So x minus 4, an absolute value, less than 1, that means that 3 is less than x is less than 5. So I certainly know that I've got convergence on the interval 3 and 5. But the question is, what about at x equals 3? And what about at x equals 5? We always have to test our endpoints here. So at x equals 3, if I were to plug in 3 to my series, I would have the series n goes from 1 to infinity of -1 to the n plus 1. X is 3, so I've got a -1 to the nth all over n. And what that boils down to is a -1 to the 2n plus 1 over n. That's just my harmonic series. 1 over n is my harmonic series. And that is a divergent series. And if that seems a bit of a foggy idea, go back to your series chapter and review tests for divergence and tests for convergence. And you'll see that the harmonic series is a known series. It always diverges. So 3 is not in our interval of convergence. At x equals 3, we're out of luck. The series does not converge. So I'm going to keep my open parentheses on the 3. All right, we've got more work to do. I'm going to make a little bit more space here. And the other piece of analysis that we need to work on is at our other endpoint here at x equals 5. So let's plug that in. So at x equals 5, we have the series going from n equals 1 to infinity, -1 to the n plus 1. And then we've got 5 minus 4, which is 1 to the n. 1 to any power is just 1, so whatever. And so this is our alternating series. You can do the alternating series test on this, and you will find that you do get conditional convergence. The point is we get convergence. So I'm just going to write converge there. So final answer for this problem, interval of convergence for f of x. We know everything between the 3 and the 5 was good. We got convergence in there. At 3, we're out of luck, but at 5, we were in luck. So we're going to have open parenthesis on the 3, closed square bracket on the 5. Okay, so we did the first part here, which was 3 square bracket 5. We now need to look at the integral of f of x. So let's do that. Now, what's lovely about these series is that both the series and its integral converge on the same interval. So let's write that down for a second. So, oops, that's not what I wanted. I wanted this. The integral of f of x and f of x have same interval of convergence, except possibly at the endpoints. So that's going to save me a lot of work. So I know for the integral of f of x dx, oops, I made a typo there. We at least have 3, 5. And then the question is, what happens at x equals 3 and what happens at x equals 5? We need to test the endpoints. So I'll do one of the endpoints here, and then I'll leave the other endpoint for you to work on. All right, so let's take a look at, first of all, what is the integral of f of x? So I basically have to integrate this series term by term. Now, -1 to the n plus 1 is just a constant, so that'll pull outside my integral. I don't even care about it, so I'm just going to copy that over. That will come along for free. It's a constant. Integrating x minus 4 to the nth power, now we're going to have x minus 4 to the n plus 1 power over n plus 1. And I still had a regular old n sitting down there below. The only thing I'm missing is my big sigma notation, so let me make a little space. There we go. Okay, so at x equals 3, let's see what we've got for the integral. I've got the sum as n goes from 1 to infinity, negative 1 to the n plus 1. X equals 3, I've got a negative 1 to the n plus 1 power, all over n plus 1 times n. And that's going to simplify to a negative 1 to the 2n plus 2. Over n times n plus 1. So that is going to be 1 over n squared plus n. And this is a convergent p-series. And so 3 is in the interval of convergence. So I know right now I can change that open parenthesis to a square bracket. You could then go through and test what happens when x equals 5. So if we want to do that, we're going to plug in negative 1 to the n plus 1, plugging in a 5. I've just got 5 minus 4 to the n over n times n plus 1. And I'll leave that piece for you to compute. And so if you go through the test here, you will find out that this does converge. And so you can change this open parenthesis to a square bracket. So here, my interval of convergence was the closed interval 3 to 5, whereas for the regular old function, it was the half open interval 3 to 5.